Welcome everyone. So today we have a seminar given online by Giuseppe Mingione from University of Parma. And it's also a great pleasure for us to follow it jointly in the seminar room. So we have participants who are in presence and participants who are remote. So the talk will be on nonlinear version of linear theories, from linear to nonlinear gradient estimates for elliptic equation. And Giuseppe, the floor is yours.
Okay, thanks a lot for the invitation. I'm very pleased to give this talk. And as you see, I'm going to give actually a survey of many of the things I've been doing over the last years, not only the recent ones. And so I will try to give an overview, and the main theme is how some of the things that are, known and classical in the linear setting can be extended to the nonlinear one. Okay, let me start from some very classical fact. So let me take the Poisson equation, and then this you can solve in many ways. And the most classical one goes via representation via fundamental solution. That's the Green's function. Okay, once you have this, you essentially have everything, because you can bound U by this Riesz potential. This is called Riesz potential, and it's a fractional integral. It's called fractional integral because the kernel is integrable. So as long as you stay far from n, the kernel is integrable. If you differentiate once, then you can go to another fractional integral, which is the I1 Riesz potential. And then if you differentiate twice, you can go this time to a fractional integral. And the difference is that these operators can be controlled by size estimates like Young's inequality and Hardy-Littlewood Pauli inequalities. While in order to handle this operator and its mapping properties, you need Caldron-Zygmunt theory and cancellations. Okay, but the main essence is that once you have this representation formula, then you know everything, in the sense that, for instance, if you want to know when U is in a certain LP space or any rearrangement in invariant function space, then you just forget about the equation and then you go to the operator, and then the mapping properties of such operators are well known. So the idea is that you disconnect yourself from the equation and you go to the operator. Now, at the first sight, this approach could seem to be completely linear, but in fact, in fact, I would like to show that this is not the case. In order to get these operators, you need a representation formula, which is, for instance, absent in the nonlinear case, but still something can be done. Okay, from now on, let me pass to this equivalent definition of Riesz potential. This is called the truncated Riesz potential. There's no trick here, it's just a cheap annuli decomposition. And this quantity, it's dominated by the usual Riesz potential when you restrict the integration over a small BR. So this quantity is more suitable if you are on bounded domains, because the previous formulas are okay if you are on the whole Rn. So from now on, the Riesz potential, for us, the Riesz potential would be the following truncated Riesz potential. So there's no, harm here. It's just another way of writing the Riesz potential. Okay. So the question I would like to pose at the beginning is the following. Now, let me get any quasi-linear equation of this type, which is at the first stage non-degenerate. So its largest eigenvalue is dominated by L, and its lowest eigenvalue is bounded from below by nu. And then you wonder if the previous formula or some equivalent versions are still okay. And then you would like to know if the previous things are still okay in the degenerate case, in the P-Laplacian case. And when I'm handling these equations, I'm just restricting, for the sake of simplicity, to the case P larger or equal than 2. In general, I'm going to consider such operators under the following growth and ellipticity assumptions, and the P-Laplacian operator is a model for these kinds of equations that are classical after the work of Lagicescu and Uralza. So in the following, anything I'm going to do when I'm handling these equations is like it's under these assumptions. Okay, what about the notion of solution? In the right-hand side, I would consider in general a measure, okay? But then there is a problem on the definition of the solution, because you do not have, when you handle measure data problems, you don't have any so-called energy solutions. So although the growth of the operator fixes a natural subbolus basis, which is W1P, then you don't have solutions that are there. So in this case, other definitions of solutions are handled, but I do not want to go into this delicate territory. Let me just say the following thing. In the following, I'm going to talk about a priori estimates. So imagine that both data and solutions are better than what they actually is in the most general case. And let me concentrate just on the shape on the a priori estimates. Then by approximation methods or by other means, these a priori estimates can be transferred to general cases where you have to handle more general cases of solutions. Typically, you go via approximations and you define solutions obtained by limiting approximations. And this is the fundamental work of Boccardo and Galloway. So Boccardo and Galloway gave the first general existence and regularity results for general measure data problems, and this work is by now classical. Then there are other definitions. Renormalized solutions were introduced by Lyons and Murat in a legendary and unpublished manuscript. Then they were also dealt with by Benilan, Boccardo, Galloway, Gariepy, Pierre, and Vasquez. Then Dalmaso, Murat, Orsini, and Pigné, they extend these notions and they give several, important results also about uniqueness. And then these solutions are finally found to be essentially equivalent for positive measures in this work by Kilpeline and Cusi and Tuola. But okay, this is just to give an overview on the notion of solutions, but I would like to point out that from now on, I'm going to concentrate just on a priori estimates, so on the shape of the estimates. Then we can go further, because the core of regularity is in the first bullet here. Okay, now the idea, let me recall, is that we have this, for the Laplacian, we have these two representation formulas, and then we want to know if something can be done in a nonlinear case. Although fundamental solutions are absent, of course. Okay, representation formulas are absent. Okay, when you pass to the linear case, the orthodoxy of so-called nonlinear potential theory, which is the theory that replaces a linear potential theory into nonlinear case, is the idea of using so-called nonlinear Wolf potentials. So nonlinear Wolf potentials are exactly like the Riesz potentials, but they do incorporate the scaling deficit of the equation. Because, of course, if you take the P-Laplacian equation, then you cannot bound U by the Riesz potential, because this estimate would not respect the scaling of the equation. So what you do, you insert at this stage the scaling deficit of the equation between solutions and data. And in doing this, you get a nonlinear operator. So Wolf potentials were for the first time introduced by Having and Mazia in a fundamental paper where they established the basic facts in nonlinear potential theory, and in fact are sometimes called Having-Mazia Wolf potentials, because they were really first introduced by them. Okay, the first result, which is very striking for general equations of this type, and just consider the P-Laplacian equation as a model, is a fundamental work by Kilpeline and Mali that tells that you can, nevertheless, the equation is nonlinear, you can pointwise bound the solution by the Wolf potential of the right-hand side, plus a localization term that comes from the fact that you are on a bounded domain. Imagine that capital I goes to 0, then if this quantity is finite, this is an integral, so it goes to 0 by absolute continuity, and then you get U less than or equal than itself. That's why you need this localization operator. On the other hand, when capital R goes to plus infinity, under suitable decay assumptions, you can delete this term because the average kills everything. But the idea is that you can pointwise bound U by the Wolff potential, which is the following one. And observe that when P is equal to 2, then this coincides with the risk potential. So the surprise is that you get an estimate via a representation formula, although convolution is not available because you are in the general knowledge. Okay. Now, once you know this, you know essentially everything on the size properties of solutions. These Wolff potentials are very useful. They are at the basic of the orthodoxy in linear potential theory because they replace risk potentials wherever you go to the P case, to the nonlinear case, and they are usually used to study, in general, delicate fine properties of Sobolev functions, capacitor issues, and fine properties of solutions. But the main point, if you look at regularity, is that, for instance, their mapping properties are known. If you know where mu is, you know where W mu is. And therefore, thanks to the previous estimates, then you can know where the solution is. The mapping properties of Wolff potentials are in turn known because of this fundamental inequality of Having and Mazia, because you can bound Wolff potential by a nonlinear iteration of two risk potentials. Nonlinear iteration means that you insert this 1 over P minus 1, because you have to, at a certain stage, this case like 1 over P minus 1, and this is linearly scaling like 1 over P minus 1. On the other hand, the behavior of risk potentials is known, therefore this composition has a well-determined behavior. And in fact, the right-hand side quantity is usually called Having and Mazia potential. Okay. Now, there were two open problems, and the first one is that what happens for the gradient? Is there such an estimate for the gradient? And the second is what happens in the vectorial case, especially for the P-Laplacian system. This was largely debated open problem. And okay, what's the difficulty in this open problem is the following one. Okay, what is this estimate? This is an estimate on solution. And in fact, the basic of Kilpelangen and Mali's proof is the George's iteration, truncation iteration. The point is that if you want to get a gradient estimate, then the first step is always the same. You take this equation, you differentiate the equation, and then you start getting gradient estimates. But wait, already when in the left-hand side you have the Laplacian operator, you cannot differentiate the equation because you are in the borderline case of Calderon-Zygmunt theory. So there are no second derivatives if the right-hand side is just in L1, for instance. So the whole procedure stops at the very first stage. Nevertheless, okay, the first answer came some years after, where in the non-degenerate case, I was able to prove that whenever you get a quasi-linear equation, you can bound the gradient via the risk potential in the non-degenerate case, exactly as for the Poisson equation. So with this, exactly as before, with this estimate at your hand, you can just forget to deal with the equation. And if you want to know what is the regularity of the gradient in terms of well-known function spaces, you forget about this. You treat the lower order term as a constant, and then you study just the mapping properties of this operator. So you just bypass the equation. And of course, when capital R goes to plus infinity, as usual, if you get a good decay property, then you get once again the usual representation formula via fundamental solutions. You let capital R goes to plus infinity, and this is as far as the non-degenerate case is considered a complete solution to this question. Okay, what happens when P is different than 2, P larger than 2? Okay, but first of all, let me tell something about the proof. Okay, what I dealt with is the following. Since you cannot, in the original proof, since you cannot differentiate the equation, So you observe the following thing. Although there are no second derivatives, as we shall see later on, the gradient can be differentiated in a fractional sense. So what you do, you prove a fractional estimate, a fractional Cacciopoli estimate on certain truncation of the gradients. So you take essentially the usual Bernstein technique and you make a fractional version of this Bernstein technique. This is very delicate because it involves a sort of nonlinear atomic decomposition that you usually do in fractional Sobolev spaces. But at the end, if you make some tricks, you can get a fractional Cacciopoli inequality. So you can bound a fractional derivative of the gradient of a truncated version of the gradient by the right-hand side. Once you have this, you can start running a De Giorgi, a fractional De Giorgi type iteration, where you improve the integrability along the fractional Sobolev embedding rather than the usual ones. Then independently, as far as the second step is concerned, independently, a similar idea was introduced by Caffarelli and Vasseur in the same year, where they have a no-local operator, and then they start using a fractional De Giorgi operator, fractional De Giorgi technique. The difference is that I have a local problem, so they have a no-local problem, and so the first step is essentially for free for them. But on the right-hand side, if you do this, then you can build up the risk potential and your representation formula. Okay, so what happens when P is different than 2? Okay, when P is different than 2, you expect that you have to pass from risk potentials to Wolf potentials according to the standard orthodoxy of nonlinear potential theory. And in fact, this was done in a first step by Frank Duzar and myself. But what is the equation telling you? The equation is telling you that if you make this, let's say, naive replacement, then you can decompose this solution as a system. So you can solve this one, hoping to get this. Of course, there's no hope in this because this one is not an elliptic equation and it admits infinitely many solutions. You can add V any curl. But if you apply this, then you look at Bogowski's theorem proof, and you know that you can represent V via the risk potential of mu. So the equation is somehow telling you something which goes against the orthodoxy of nonlinear potential theory, that is, you can bound the gradient once again via the risk potentials. So rather than the usual Wolf potentials that are always in use when you go to nonlinear theories. Okay, this might seem very brave, but in fact, it turned out to be true. And in the general nonlinear case, after a first estimate we got with Frank Duzar in years before, then we were able to prove that no matter the equation is nonlinear and degenerate, you can bound du to the right power, because the power must be there to respect the scaling of the equation, by the risk potential. So the effect of this estimate is that you can reduce the integrability and the regularity theory of any quasi-linear potentially degenerate equation to the Poisson equation. Because if you want to know whatever du is, then you look at the risk potential and then you're done. And this catches up all the possible estimates on of these equations without changing the techniques, because you don't go to equations anymore. You just treat it as it were linear. Let me give you an example. And of course, there's another way, a more suggestive way to write down this estimating, a more intrinsic way. And then you can bound what is under the symbol of divergence with the risk potential. So it's like Bogowski's theorem. You can apply the risk potential to both sides, and then you can bound what is under the symbol of divergence with the risk potential. So it's a complete linearization of this equation. Okay, as a corollary, you can get, for instance, a nice representation formula if you get proper decay additivity. So it's exactly like linear. So you are reducing any quasi-linear equation to the linear case. And let me give you, for instance, a few corollaries. And okay, how this is done, the proof is very delicate. It involves a lot of course, we took advantage of a lot of work, like, for instance, the basic work of Boccardo Galloway, Dalmaso, Murat, and other people. But then we combined everything in the realm of nonlinear potential theory, and then we were able to get this final estimate. So let me give some corollary. For instance, just take the interior estimates for this model equation, just to stay simple. Okay, for instance, there are well-known results on the higher integrability of the gradient when mu is very good by Ibanez and Di Benedetto Manfredi, and they follow as a corollary. Then the classical theory of Adams on Morey spaces then can be follows immediately because you are just now treating it as the Poisson equation. And then the classical interior estimates of Boccardo and Galloway, they can be obtained by using these estimates. Of course, we of course are we are based on the work of Boccardo, Galloway, Vasquez, and other people. And then the classical estimates of Talenti via rearrangements, they follow in the interior version, just essentially because now the equation is like the Poisson equation for us. Okay, what about the vectorial setting? The vectorial setting is a different story. The vectorial setting, first of all, if you want to get such an estimate for a general quasi-linear system, then it's not an easy matter. It cannot be true because for systems, even when the right-hand side is 0, for general systems, you can get singularities. You can get unbounded solutions just because the problem is vectorial. And actually, there is no measure theory. There is no real general theory for general elliptic systems involving measure data. So what you do to get these estimates, you go to special structures, like for instance, the P-Laplacian system, or usually Uhlenbeck structures. And then we still were able to prove the same results. And the proof is a completely different story. And it's very, very long and difficult. It essentially exploits every single bit of regularity theory of P-Laplacian operators and the generate equations. But still, we were able to solve both the two things. First, the estimate of Kilpelangen and Mali is now found to be true also in the vectorial case. This was not known before, and the gradient estimate holds for solutions to this kind of systems. The proof is very difficult, but it involves essentially the same corollaries as before, plus some benefits. For instance, if you take once again the P-Laplacian system, and if you look at interior estimates, for instance, the theory built up by Dolzmann, Ungenbrüller, and Müller for this kind of systems, then it follows as a corollary. Of course, once again, we are using everything was done in the field. And then the classical theory of measure data problems of Boccardo and Galloway was not developed in the vectorial case because the proof is purely scalar in that case. You need truncations, you need essentially the ghost of some maximum principle that for systems is absent, but now you can uplift this, you can upgrade this theory to the vectorial case. And also the classical theory of the classical estimates of Talenti via rearrangements then can be done in the interior. And all these things, they just follow in one shot. So the proof is very delicate because we have to match the classical things from vectorial regularity theory, so epsilon regularity theorems, Uhlenbeck theorem, and so forth, to nonlinear potential theory. So we have to make a bridge between these two things that were not talking to each other before. And in particular, we need a very weak version and a nonlinear version of the classical harmonic approximation lemma of de Giorgi that could be of interest in several other applications. But the outcome is that you have these two estimates. So let me tell you once again, first of all, just one thing that could match these estimates with some classical mathematics that was made in Paris in the 30s. Okay, let me pose one question. Okay, for how many x this estimate is valid? Usually you say that it's valid almost everywhere. Actually, I say that it's valid everywhere. In which sense? As an outcome of our proof, we can prove that if the risk potential is bounded, then du has a precise representative at that point. So you have two options. If the right-hand side is infinite, then you just do not pose the problem. If the right-hand side is finite, then you have that du has a Lebesgue point, and then you know how to interpret this value. So in this sense, this estimate is valid for every point. And this is the nonlinear version of the classical fine properties properties of solutions obtained by in the classical linear potential theory in the schools by Choquet, Denis, and other people. So we are also able to prove these fine properties of solutions in this setting. Okay, let me get some relevant corollaries that could be of interest. Okay, first of all, let me go back to the risk potential estimate that I showed you before, this one. You can bound for any general equation. Now let me go back to the scalar case. You can bound du by the risk potential. So as a corollary, if the risk potential is in L infinity, then the gradient is locally bounded, essentially bounded. And this is a trivial corollary. So if the risk potential is bounded, then the gradient is bounded. Of course, this is an integral. If you recall the definition of truncated risk potential, it's an integral. So if it's locally bounded, when capital R goes to 0, this object goes to 0 pointwise, almost everywhere. And now, this provides a first answer to a very classical open problem in the theory of this quasi-linear equation. So find the minimal assumptions on the right-hand side for which the gradient is bounded. There's an old conjecture by Nina Uyaltseva, I was told that it belongs to Nina Uyaltseva, that told that the property of mu that guarantees that the gradient is bounded is independent of P. Of course, probably Nina was thinking to the P Laplacian operator. And now this property is independent of P and even on the operator. So this confirms this conjecture. But even more, you know that if this object is bounded, then this quantity is almost everywhere going to 0 when capital R goes to 0. If you strengthen this into uniform convergence, then you prove that the U is continuous. Because basically, the effect in these open problems is the following one. When solutions are bad in measure data problems, when measures concentrate on sets with small house of dimensions, small capacity, so that in a sense, the equation is not rigid enough to detect these singularities and these sets, and the singularities can occur on such small sets. It's typical to construct these kinds of solutions using Frostman lemmas, for instance. So the idea is that if the measure concentrates on small subsets, then singularities occur. So this prevents the measure to concentrate on two small subsets. And if you look at the definition of the risk potential at the denominator, there is rho to the n-1. This, for instance, tells that the measure cannot concentrate on sets with Hausdorff dimension, which is smaller than n-1, which is the borderline capacitary case in this case, in these problems. And the difference between being bounded and being continuous, it's exactly measured by how the measure, so how the kernel of the risk potential goes to 0 against the higher measure with respect to the product. Because the risk potential is mu of b rho over rho to the n-1 integrated against d rho over rho. So this is a very fine criterion and gives a first answer to this old conjecture. It's a very long open problem, the one of determining the best conditions on mu, telling you that the solutions are Lipschitz. Okay, now let me give a funny application, which goes, which is coming back later on. Okay, there's a classical theorem of Stein, which is actually the borderline version of Morray's embedding theorem, that tells when V is continuous once you know where the gradient is. Okay, this is Morray's theorem. You know that when dV is in Ln plus something, then V is in this Hilbert space. It's once again a matter of risk potentials. Why? Because usually you represent V via the risk potential of the gradient. So if the gradient has a certain integrability, that is its associated measure as a decay, then you can get the regularity of V. Now, what happens when epsilon goes to 0? When epsilon goes to 0 and you use just the Lebesgue scale, you go to Ln. But Ln is not sufficient to get continuity of V, because in that case, solutions are merely BMO, that's vanishing mean oscillation solutions. BMO, it's the closure of smooth functions in BMO, the bounded mean oscillation space of John and Nirenberg. So the borderline space, it's a space which is slightly smaller, or smaller, it depends on the taste, of Ln, but which is still larger than any Ln plus epsilon space. This is Lorentz space, and it's described by prescribing the level set decay of the function G. These are interpolation spaces. So therefore, Calderon-Zygmunt theory applies and gives the following essentially equivalent statement of Stein's theorem. If you get the Poisson system and the right-hand side belongs to Ln1, then you know that the gradient is bounded. So in terms of rearrangement function space, you can prove, this is a paper of Andrea Cianchi at the beginning of the 90s, that this is the best rearrangement invariant function spaces in order that guarantees this property. So that is it. There's nothing more, I mean, nothing more. Now, what are a typical example of Lorentz function is the following one. You take 1 over x, which is naturally Marcinkiewicz-n, weak Ln, and then you correct with the log, which is the first function popping up in your mind to correct this kind of borderline non-integrability issues. It's classical, it's natural, because if you look at this case, when epsilon goes to 0, you get that dV is in Ln, and V is a vanishing mean oscillation. VMO functions can be unbounded, but with a log blow up. Therefore, you correct the potential log blow up created by Ln by adding a log. And typically, a log in the right-hand side gives a better regular solution because of the stability of elliptic equations. I mean, elliptic equations are stable under perturbations of data in any respect, and this is just another example. Okay, now the catch with the nonlinear theorems I was stating before is the following one. If mu is in Ln1, then in fact the risk potential goes to 0 uniformly. And then you can apply our theorem. And so you pass from the classical Stein's theorem that tells you when solutions to the Poisson systems are integrable. There should be a minus here, sorry. So you pass from the linear Stein's theorem to a nonlinear Stein theorem that tells that if U solves this, then the U is continuous, in particular is bounded. And so in terms of function spaces, this is the full solutions to this old conjecture of Ural-Alzheimer that tells that conditions for which the gradient is bounded should be independent of P. Here it's independent of P because Ln1 is independent of P, and it actually is independent of any operator. So this is just another example of how these kinds of theorems and these theories are linearizing this equation. So in a sense, you are just linearizing the equation. Okay, so we have seen an analog of representation formula via risk potentials for U, for the gradient. And let me give just a brief example of how, in a sense, singular integrals are still there also in measured data problems. Okay, for this, I want to introduce these fractional sublet spaces. There's really no need to do this in Paris, especially these days, because these spaces became extremely familiar. So there are infinitely many ways you can say that a function is fractionally differentiable. A classical ways using these Slobodevsky spaces and Gallardo norms. So the idea is that you take a parameter here, S and gamma, and then you say that the oscillations of V measured in an L gamma way are small enough to compensate the blow up of this kernel. So these are just fractional sublet spaces. They are what they are in this case, like, oh, there's a typo here. This should be S, sorry. Okay, in other words, this is a way to prescribe Elder continuity in L gamma space. There's a more precise way to do this using something called Calderon spaces of Devore and Sharpley, but I will not go through this. Okay, anyway, these are sublet spaces. Okay, classical theory of Calderon-Zygmunt. Laplacian belongs to LQ, and the second derivative belongs to LQ. So the classical theory of Calderon-Zygmunt switching from Laplacian to the Hessian. That's the theory. This is classical. SQ is different from 1 and plus infinity. This doesn't work in the case we are interested in, that is the right-hand side is a measure. So essentially, you see, Calderon-Zygmunt theory is that you can switch divergence. You can replace divergence with the full symbol of the gradient. That's the idea. Okay, now we would like to know what happens in the to measure data case already for nonlinear equations in the non-degenerate case and also in the degenerate case, keeping in mind that the gradient cannot be in W11 by counterexamples. So in a certain sense, the analog, the singular integral analog of the previous theorems is the following one. We were able to prove once again that what you have under the symbol of divergence belongs to W sigma 1 for any sigma before 1, before the forbidden one, which is 1. So if you look at the Laplacian case, what you have under the symbol of divergence is du, and du cannot be in W11. Still, we prove that du in that case is in W sigma 1. This is optimal because actually, if you look at the fundamental solution representation for the Poisson equation, and if you make some computations, you see that du doesn't belong to W11, but it belongs to W sigma 1 for every sigma before 1. And so this is the nonlinear analog. It's the intrinsic nonlinear analog of the theorem. So why do we formulate this integral, this result in this case, using this vector field? Because the equation is degenerate. So if you look at the whole vector field, this compensates the generation of the equation. So in a sense, this is the same phenomenon that happens in the linear case via fundamental solutions. And the proof is very delicate. It involves, once again, delicate nonlinear atomic decompositions, where in these atomic decompositions, you don't use harmonic functions as atoms as usual, but you use solutions, different atoms that are themselves solutions of homogeneous nonlinear equations. So there's a complete linearization of the equation with respect to differentiability. And it's a similar phenomenon that you have for the Riesz potentials. In particular, this implies as a corollary an old result of mine in this paper, where I proved that for measured data solutions, then the gradient is in W sigma 1 for every sigma less than 1. So this is the upgrade. So why do we need to formulate this result in terms of the whole vector field? Because otherwise you don't catch the borderline limiting regularity, because the equation is degenerate. And in fact, if you look at the P-Laplacian equation, in general, solutions are not expected to be differentiable with so high level of differentiability. In fact, it implies this result, which is sharp. So if you look at the when P is larger than 2, you don't get W sigma 1 because the equation is degenerate, and then you don't get any exponent of differentiability. This is the same phenomenon when the right-hand side is 0, and then you get that the gradient is C0 alpha, but not for every alpha, because the degeneration kills the rate of oscillations. So it kills the rate of oscillations at the Hilbert level, and it kills exactly in the same scale of differentiability, which is fractional differentiability. Because fractional differentiability is Hilbert continuity in L gamma spaces, in Lebesgue spaces. So therefore, when the equation is degenerate, you don't expect the full range of differentiability. So it's exactly the same phenomenon when you look at interpolation scales. But it's like in complex analysis, you get a function which is not analytic, but if you raise it to a higher power, it becomes analytic. So if you look at the whole object, which is under the symbol of divergence, then you recover the full differentiability because you incorporate the degeneration. So in some sense, it's like considering these kinds of equations as two ways. This can be considered a nonlinear equation in the gradient, but it can also be considered a linear equation in this nonlinear vector field of the gradient. And in that case, it can be read as a linear equation. So it's just another way of looking at these equations. And in fact, the analogy with potential estimates is complete, because for potential estimates, we can bound this by this fractional integral of the right-hand side. While if you look at differentiability, we have this perfect Cacciopoli typing equality where we bound the Gallardo norm of what is under the symbol of divergence by the vector field itself. So it's a complete analogy. So that's the third estimate via singular integrals. So the entire program here is to take these equations and to show that they, in a sense, become linear equations. So finally, the last part of the talk is more recent stuff, and this is joint work with Lisa Beck and from Augsburg and Cristiana De Filippis from Torino. Okay, what about non-uniform ellipticity? Okay, let me just consider the variational case, because in the non-uniformly elliptic case, but the variational setting is very common, and it provides you a complete and ambiguous definition of solution. Okay, let me take this variational integral. And the Euler-Lagrange equation is exactly of the quasi-linear type that we saw before. Now, when non-uniform ellipticity occurs, if you take the P-Laplacian equation, the P-Laplacian equation is degenerate, but it's still uniformly elliptic, because the highest eigenvalue is bounded by du to the p minus 2, z to the p minus 2, and the lowest eigenvalue by the same quantity. So the ratio is bounded. And the ratio is the quantity that occurs in regularity estimates. That's the quantity you need to know that is bounded to go on with the estimate. Okay, the ellipticity ratio that I call RZ in non-uniformly elliptic problems goes to plus infinity when the gradient goes to plus infinity. So there's a competition, because you would like to know that the gradient is bounded, but in order to prove that the gradient is bounded, you need that this quantity is going to plus infinity, but on the other hand, this is going to plus infinity when the gradient tends to be unbounded. And this is the main difficulty in so-called non-uniformly elliptic equations. And there's a giant literature, classical literature. These are people that worked on non-uniformly elliptic equations in earlier times. For instance, minimal surfaces operators are non-uniformly elliptic operators. And Trudinger's thesis is on these operators and so forth. And these are more recent papers, and in particular, there's the fundamental work of Zhikov in homogenization, where he considered a lot of homogenization problems for non-uniformly elliptic operators. Zhikov's papers and these Russian papers are really a treasure that are that need to be rediscovered. And there's a monograph by Ivanov where there are, let's say, an account of nonlinear uniformly elliptic literature up to the 80s. And this was especially developed in St. Petersburg school. And then there are these pioneering papers by Marcellini, where he started at length with some striking estimates in the variational setting, these non-uniformly elliptic problems. And let me just give the problem I would like to discuss. So we have seen that in this uniformly elliptic case, there's a universal role played by this Lorentz space in order to get Lipschitz continuity. Now we want to know what happens in the non-uniformly elliptic setting. So we want to know if the real structure, the very structure of the equation, that is, you are considering what is under the symbol of divergence, is playing a role also in this setting. Okay, how do I consider? Okay, there should be identity matrix here. I just take this, let's say, more cool notation. So let me describe. That's the basic assumption you do in non-uniform ellipticity. So G1 and G2 are the two eigenvalues of the second derivatives matrix describing ellipticity. So the ratio, the ellipticity ratio, is bounded by this quantity. And the main assumption that is done in the literature, which is actually unavoidable, is that this ratio is allowed to blow up, but cannot blow up as a too larger power of this intrinsic energy, which is the energy that is associated to the operator and dictates the coercivity rate of the operator. For instance, if in the P-Laplacian case, G1 is z to the p minus 2, therefore this quantity is exactly z to the p. Okay, the nice and surprising fact is that the Ln1 is really a universal space for Lipschitz continuity. So whatever non-uniform elliptic operator you're getting, then the result is always this one. And both in the scalar and in the vectorial case, whenever the right-hand side is in Ln1, still you get Lipschitz continuity. So this is really a universal space for Lipschitz continuity in any respect. This estimate might appear a bit technical, but it actually reduces to the usual ones in every possible model case. And once again, we are plugging these nonlinear potential theoretic techniques in these settings, and we get a new approach to prove estimates that simplifies actually the previous ones. In particular, the previous estimate gives you back the standard estimate we have seen before in the P-Laplacian case, gives back the classical theorem of Marcellini when you have that the eigenvalues grow with different polynomial settings under the same bounds of Marcellini. So it gives you so Marcellini did not have this right-hand side. So now our aim is to get sharp estimates also with the right-hand side that are sharp with respect to the function space considered. And we can also deal with exponential and fast growth conditions. For instance, take these integrands with very fast growth that have been used, for instance, by Duke and Eels in harmonic mappings, by Craig Evans in weak KAM theory to approximate L infinity. And then we still are able to prove always the same result. So it's really a universal space. Okay, finally, let me get to the second problem. That is, what happens when you add coefficients? Because the interaction between coefficients and non-uniform ellipticity is problematic. So it's not like Schauder theory. So in non-uniformly elliptic settings, Schauder estimates might fail. You get a perfectly nice operator, you add coefficients which are elder, and then solutions can be irregular nevertheless. So there are more delicate conditions. And this is recent work with Cristiana De Filippis. I do not want to go into general statements because they are very technical, but these technical statements, when applied to the single model, relevant model cases, they always give sharp results. So I will consider finally an operator with this PQ growth, that is the two eigenvalues grow with different polynomial rates, like Marcellini's theory. Functionals with fast growth conditions, and uniformly, once again, uniformly elliptic operators. This is uniform ellipticity in this setting, like the P Laplacian. And what happens here is that in the first case, you describe lower and higher eigenvalue, and you require that C belongs to this W1D space. So it's a Sobolev coefficient. Sobolev coefficients are very well considered in the literature, and this implies that D is larger than N, so therefore C is Hilbert continuous, as it must be to get Lipschitz continuity at least. And so we prove with De Filippis that once again, Ln1 plays a role, but the rate of differentiability must be such that this quantity is not too larger than 1. This is an essential condition because otherwise this result fails. And for instance, if you do consider the Zhikov functional, the double phase functional, which is like the P Laplacian when A of x is 0 and A of x is larger than 0, it belongs to LQ, that's the same condition. And so this gap bound tells that the rate of the highest and the lowest eigenvalue cannot be too far from each other because it must be a bit larger than 1. So in particular, if the dimension goes to plus infinity, then the two rates, the non-uniform ellipticity must disappear. And if coefficients are not regular enough, that's the same story. This bound is optimal as considered in this case. This is a theorem that I obtained with Maria Colombo and Paolo Baroni. And this is a sharp theorem. It's a functional considered by Zhikov in the setting of homogenization of a strongly anisotropic material, and tells you that the gradient is Hilbert continuous if and only if this bound is satisfied. So Q over P cannot be larger than 1. Cannot be too larger than 1. It's larger than 1, but not too larger, depending on the rate of coefficients. And in particular, if this inequality is not satisfied, then solutions are irregular. So that's a failure of Schauder estimates in the non-uniformly elliptic case. And the catch between this condition and this sharp one is the following one. You know that if A of x is in W1D, then it's also Hilbert continuous by Morris embedding theorem, and the two rates, they do coincide. So the previous bound in the realm of Sobolev spaces is sharp. And finally, the last result I'm going to talk about is this one. And here there's really a surprising fact. When you switch from non-uniformly elliptic problems with polynomial rate to fast problems, you would expect that you have to strengthen the coefficients regularity, but it's actually the opposite. You need any D, not quantified in terms of rate, any D is sufficient. Dealing with these functionals is very difficult technically because they do not satisfy the delta 2 condition. Although philosophically it should be easier to prove Lipschitz regularity because you're penalizing a higher level, higher rate energy. And this reflects on the fact that you need less regularity on coefficients. So in a certain sense, although the rate of non-uniform ellipticity is stronger, you are closer to the uniformly elliptic case because you have to renormalize with respect to the energy itself. And this holds for any general composition of exponentials with coefficients. There's a very general theory proposed in this paper that covers essentially all cases. And in particular, finally, when you have a uniformly elliptic setting, you go back to the usual space. F is in Ln1, but also the derivative of coefficients. So that's the story. That's the final story. That's when you go to PQ, then you need that the gradient of coefficients is in a larger LP space. When you have exponential fast growth conditions, and surprisingly, you're approaching to the uniformly elliptic case because the energies are growing very fast, then you need any LD And then in the uniformly elliptic case, you go back to the standard case. And this is new already for the P-Laplacian case. This was not observed before. And then finally, this gives an immediate application to an old problem, that is finding the best possible conditions in obstacle problems for which the gradient is bounded. Once again, if you minimize any of the functions I showed you before under this condition on the obstacle, then the gradient is locally bounded provided the second derivatives are in Ln1. This was proved and known in the polynomial case when the gradient, the second derivatives of the obstacles are L infinity, but this was not known. And the intuition is that when you linearize obstacle problems, you go essentially to the previous equations, and then you can apply our theory. So this is actually a corollary of our general results. Because you linearize the equation, then the Euler-Lagrange equation of an obstacle problems can be written in the following form. So if you are on the contact set, if you are not on the contact sets, then the right-hand side is 0. That's the characteristic function. Otherwise, it is an identity because on the contact set, the gradient is equal to the gradient, and you can write down in the following way. But if you know that the gradient has second derivatives, that the gradient, the obstacle has second derivatives, you can expand this, and you can write exactly as a right-hand side in Ln1. And this is a general theory, and the proofs are very long, but I'm not going to talk about that. Okay, thanks for your attention, and sorry for taking longer time.
Thank you. We are actually on time. We have time for a question, either from remote participants or from the room. So please go ahead. Yes, Antoine has a question.
Hi, Rosario. I have a question on the Calderon-Zygmunt estimate.
Who are you? I mean, is Cyril?
No.
Oh.
Antoine Gloria.
Antoine.
Ah, okay, Antoine. Sorry, I mean, these masks. Okay, actually, I see just one dot in my screen. No.
Sorry. So yes, I was wondering for the Calderon-Zygmunt estimate. So what you showed is if divergence A grad U equals something, then A grad U is nice, depending on the something. And my question is, usually, sometimes you're interested in differences, like divergence A grad U minus divergence A grad V equals mu. In the linear case, that's the same because the operator is linear, so you can estimate the difference. And for monotone operators, you test with U minus V. Yeah. And by monotonicity, you get the bound on the LP norm if you have the P-Laplacian. And I was wondering, for the Calderon-Zygmunt estimate, would you have the same kind of stuff?
Well, it's a difficult question because, in fact, to prove this, we need to get differences, because what we do is we take these nonlinear atomic decompositions and we make a comparisons with the solutions to homogeneous equations. But then this leads to the fractional differentiability of A of du. The fractional differentiability of the gradient is a different story because probably you need more than monotonicity.
Okay, a question. Maybe I have a naive question because so in your so you have this nonlinear version of Stein's result, and you keep saying that the Lorentz being in the Lorentz space is a sort of minimal condition. But by this, you don't mean that it's a necessary condition, but
no, it's okay. In the Poisson case, it's necessary.
So, but you mean if you drop a little bit of integrability, like if you go to the standard LN space, all these results cease to be true for any P?
For any P, is not known, but it's expected to be.
Okay, I see.
Because the idea is that the problem is linearized in a sense.
It's not going to help.
For the Poisson equation, okay, for any P, I mean, because you see, for any P, when the gradient is large, that is the critical point, what happens? That the equation becomes a Laplacian. So if you do consider the Poisson equation, the P Poisson equation, right? The first eigenvalue is du to the P minus 2. Okay, the problematic point is when the gradient is large. But when the gradient is large, the equation is becoming like Poisson. So this is expected to be optimal. It's optimal certainly in the Poisson case. So in a sense, what we prove is that all these kinds of equations and systems, they behave as linear. It's like linear equations.
Questions maybe from the remote participant? You can raise hand, I think. Let's see. Is there someone who's raising hand? Oh, no, these are comments. These are comments. Oh yeah. So Michael Goldman asked, is there something for non-divergence equations?
We have, okay, for full linear linear equation, okay, non-divergence equations, you mean, for instance, full linear linear, right?
Yeah.
Okay, full linear linear are actually easier to deal with because there is no, the whole point in these problems is that you have to keep track of the degeneration of the equation because you have a degenerate equation. If you get a full linear elliptic case, we have a paper with Toti Daskalopoulos and Tomo Cusi, and it's where we prove essentially the same thing using a different kind of linear potential, of nonlinear potentials. And we once again have that, for instance, if you have a full linear equations like f of the Hessian equals to f, then if f is in ln1, then the gradient is bounded. But it's a much simpler proof. It's a much simpler proof when you apply this approach. I didn't talk about this full linear because I did not want to put too many ingredients in this soup.
I don't know if Michael, you want to make more specific your question or?
Thanks. That was more as a question.
Okay.
Sorry. So I have another question. So
yes, as many as you like.
You switched from the equation to minimizers. I didn't really catch why.
I can tell you why, because the idea of solution for these kinds of equations for the model cases is not well defined. For instance, if you take such an operator, just to give you an example, if you take the Euler Lagrange of this operator, where are you getting solutions, W1P or W1Q? So in all the literature, there are actually two approaches. The first approach is the following. You start from W1Q, and then you prove that it's more regular. But W1Q is not the natural space. On the other hand, you can prove that if you take any general solutions, you pass from, let's say, from regularity theory for any general solutions to existence of one regular solution. So you take the Dirichlet problem and you prove the existence of one regular solutions. But otherwise, there is an ambiguity on the rate of solutions, on the rate of integrability of solutions, on the degree of integrability. It's classical in the literature. This ambiguity disappears when you have minimizers. I could have also talked about equations, but it was, I mean, easier to directly talk about minimizers.
Thank you.
Other questions? Zoom, remote? No, so if not, thank you very much.
You're welcome, thank you.
And those who want can stay a little bit more online. Maybe we can stop sharing your screen and I will stop the recording.